Hey everybody, hope you're having a good night. Um, so I'm making a new practical networking video series that kind of goes over different real world scenarios, and how your practical knowledge in networking can help you address any of the problems that you're um, maybe presented with, or maybe you need to craft a solution for. So this is something that I ran into in the real world for my day job, where we had work that was being done on a link, one of our transit internet links, and we needed to fail the traffic out of the site for that specific link and kind of just migrate traffic over from one ISP to another. That way we can minimize any disruption to the services that we host. So I thought that was kind of a fairly straightforward sample problem that we can kind of bite off and chew on for the beginning of this series. And if there's any other scenarios that you're particularly interested in, you can let me know, and I'll see if I can make a video on that. But today we're going to set up the lab environment, get everything configured, and basically test and validate the different options that are available in order to do something like this. Um, so the first thing we're going to do is we're going to set out our topology. We're going to grab a couple of routers here. We'll grab 4 of them. We're going to need a couple of servers as well. And to make the management a little bit easier, we're going to do an external connector to my local network. That way I can manage it through a local secure shell client instead of going through the console here, which is pretty slow. So let's go ahead and rearrange these. And we'll label them. So we'll say this is router 1. This guy will be, say, router 3. Router 2. And router 4. And we're going to have a server up here, server down here, and we'll put the unmanaged connections out to the side. So if we connect these guys together, let's see. Oh. This UI is kind of buggy. Router 2 to router 3. This UI kind of bugs out a little bit, so I may have to show and unshow the links a couple of times. It's kind of weird. Okay. And so we'll rename this guy as the server host. This is going to represent the services that live in the service provider environment. And we'll say that this is the client host. So this will be the client that's trying to reach out to the server environment. So simply put, if we just put something down here, we'll say that this is the client. Make this like a red. There we go. Then we'll say up here is the server. And we'll add a link from router 1 over to the server. So it'll be gig 3 to see what interfaces we have here. Actually, I want an Ubuntu host, so let me actually delete these nodes real quick. Delete. Make it a bit easier so we can run a continuous ping from the command prompt when we do our testing. There we go. So from router 2, this will be Gigi 3. Then on this guy, we're going to create a separate interface as well. And I'll go to the out of band. What I reference as the out of band anyway. Okay, and then router 1, we need to add a link from Gigi 3 to ENS2. And ENS3, that's good. That's fine. And this is going to be a bridge. Okay. Show links. Hide these links. Okay, so this is what our topology is going to look like. We'll rename this guy as the server. And this guy will be the client. And we'll put his host name as client. Okay. All right. So we should be good here. Go ahead and start all this up. All right, so while this is all booting up, let me load some consoles here. Router 1, router 2, 3 and 4. Alright, so we'll wait for all these devices to come up. So in the meantime, while we're waiting on those to come up, we'll kind of talk about what we're going to be doing here. So we can see from this topology here that we have router 1 all the way at the top. This represents our service provider environment where we have a server which is hosting some service, and it needs to be reachable through one of two links, either ISP1 or ISP2, which is router 3 and router 4, which I should probably designate here. So we'll say this is ISP1. And ISP2, okay? So the general idea is that we have router 1, which is the service that we need to reach, that needs to be redundant and highly available. So if there is work that's being done on ISP1 or ISP2, the traffic should just be able to come in on the other link without there being any sort of loss of service. So there's a couple of different options that are available when it comes to the failover and what we can do. So the first thing that we could do is actually nothing. In a highly available design, you should already have redundancy in place in terms of physical hardware, diversified carrier links. If that's the environment that you're operating within, that should already be there, and the failover should already be baked in. So one option is that you could actually do nothing, and you can just let the maintenance happen on the link, for example, and traffic should just fail over as designed. Now, if you don't like that idea and you just want to be a bit more proactive, what you can do is there's a few other options from here. You can revoke the advertisement of the subnet from one of the ISPs. So if we're connecting to ISP1 and ISP2, let's say number 1 is the one who's going to be doing the work and we don't want any traffic coming into our network over that link, we can simply retract our advertisement for our network, for this server network, from ISP1 so that it's only reachable through ISP2. That way, naturally, all of the inbound traffic will just come through ISP2, and at that point, you don't have to worry about any work that's being done on ISP1's link. Once they're finished, you can then start propagating the advertisement again. So that's one way that you could do it. The other thing that you can do is, instead of retracting the advertisement, you could do an AS path prepend, where you effectively add on multiple ASNs to the existing path. So if you're not familiar with BGP, you have an autonomous system number that gets assigned to every router, every autonomous system. So in this case, we have 4 routers. So for this use case, there will be 4 different autonomous systems. And part of the path selection for BGP is looking at the AS path. So as an advertisement is propagated throughout a network, that router that is propagating the advertisement will append, or prepend rather, their ASN to the advertisement. So for example, if we have a scenario where this is ASN 1, 2, 3, and 4, when 1 advertises it to ISP1 and their ASN is 3, when they get that advertisement, they're only going to see the 1 value. But when they go back and advertise it over to router 2, for example, when router 2 gets it, they're going to see the ASN as being 3 and then 1. So there's a complete pathway that BGP can see for who was advertising this network to them, and then who advertised it to the neighbor that they learned that route from. And primarily this is used for like a loop detection mechanism, but it could also be used for cases where we want to prefer one path versus another. When you have, say, if you have a route and there's 5 ASs within that pathway, and you have the same route, but there's maybe 2 for the AS pathway, the one with 2 is going to be more preferred, because theoretically there's less hops to get to that remote destination. It's a more optimal path. So using this method, you could actually say that even though you still have the routes and you still propagate the routes through ISP1, you can make it look less desirable, so that when the traffic gets routed into the network, instead of going in this way, it'll go over this way. So that's AS path prepending. And the third option, which is not, I won't say it's not typically recommended, but it requires coordination, is using community tags. So you can kind of do the same concept with ASPath prepending, where you take whatever route that you want to look worse and propagate that throughout the network. Instead of doing that, what you could do is within your advertisement, you can set a community tag. And it's just a numerical value that's separated by a colon. So you may see it as, for example, 123:456, something like that, right? But when you advertise that to your peer and it sees that community tag value, this has to be coordinated in advance, but you can have an agreement with the ISP that says, hey, if I send you this community tag, then this is how I want you to treat the route. So you can tell them that, hey, if I send you this community tag, I want you to prepend that route for me with your ASN and make it look worse than what it really is. So if I didn't want to do the prepending myself, what I could do is just attach that community tag to that route. And when it gets advertised out to ISPA and ISPB, 1 and 2, whatever, the one ISP, because it has that agreement with you, when it sees that community tag, it's then going to add its own ASN to that pathway and make the route look worse when it gets propagated down to router 2. So instead of router 2 going back up through ISP 2, it'll instead take the route through ISP 1. And those are the 3 basic ways that you can basically do this. So let's see if all these nodes are back up yet. Okay. So we're going to go ahead and start configuring things here. So first thing, we'll set the host name to router 1. And what we'll do is we'll just get the basic secure shell connectivity working. That way we can just manage it through secure CRT, and it's going to be a lot easier than having to do it through this console connection, which is kind of slow. So we'll say AAA new model, username Cisco, privilege 15, password Cisco. This is just setting a username and password to access the device with super user privileges, basically. We'll need to set the IP domain name so that we can generate an RSA key for the SSH authentication. And then we'll say enable password is Cisco as well. So we'll say crypto key generate RSA modulus 2048. So this will generate a key pair. That way we can authenticate using SSH. And then what we'll do is say line VTY04 transport input SSH. And then what I'm going to do is I'm going to set the timeout to be 60 minutes. That way the secure shell session doesn't time out unexpectedly. You wouldn't do this in a production device, but obviously it's lab, so, you know, who cares? Okay. That's done for this device. Name router 2. And let's say crypto key generate. Okay, so we'll say that for router 3 is AAA new model, username Cisco, privilege 15, password Cisco, IP domain name is cisco.com, and we'll set our enable password to Cisco as well. All right, crypto key generate RSA modulus 2048. Okay. Yeah, and that's another reason why I want to get into the secure shell. Then we don't have to worry about all these console messages. It can get pretty annoying after a while. Let's see. So IP domain name cisco.com. All right. So crypto. List. Okay, so I got the basics for SSH on these devices so far. Now I need to assign IP addresses for the out-of-band management. So for what I refer to as the out-of-band management. So I'll be attaching this to my local network through an external connector here, because I'm using a virtualized environment. So I need to bridge that communication pathway. So I set up an interface off of all these routers to go to a external connector to bridge it to my local network. I need to do some IP addressing and routing to get that operational. So we'll do for router 1 is interface gig 4 will be IP address of 192.168.8.1. And then what we'll say is I need to set up routing as well. So we'll do IP route for the 192.168 network to the local gateway. Now, if I pull up a command prompt, bring that over here, 192.168.8.1. So now I got reachability to that host. And then if I do a secure shell, 8.1, and my username was Cisco. Accept. There we go. So now I have a remote session to Cisco, to that router, right? So let's go ahead and do that again for router 2 as well. Interface gig 4, IP address of 192.168.8.2. Shut. Okay. So let me see. Did I set the enable password here? Enable password Cisco. Okay. There we go. It was my fault. Okay. All right, so that should set us up for secure shell into the routers. Let's add in another one here. 3. There we go. All right, so we have remote access to all of those. So let's see what else. The servers. So we need to be able to get into the servers as well, right? So start pulling up those consoles and get that connectivity, and then we can kind of go over all the failover stuff. Nope. So username and password is Cisco by default. Okay. So let's see. This is the server. So for the Ubuntu host, there's typically a Etsy netplan host file with the configuration. So we'll have to go in here and 550. Okay. I can't read that. There we go. All right. Let's see here. So we're doing DHCP, which we don't want to do since we have specific IP addresses that we're going to want to use. So we'll take that out and we'll put in the IP addressing that we're going to be using. So we'll say for addresses, we're going to use 192. Actually, we'll do 10.10.10.10. Why not? /24. Then we'll say for the default gateway, it's going to be 10.10.10.1. Yeah, because we're on the server. Yep. And then we'll say for ENS3 for the out-of-band connection, the DHCP4 will be false. The address will be 192.168.8.6, I guess. And we'll say that for the gateway is 192.168.8.254. Save that. Then we'll say sudo netplan apply. Okay, so that got added. IP route show. So we're gonna have to do a similar route here. So sudo IP route add for 92.168. 0/16. The 192.168.8.254. Okay. So we'll see if we can ping this guy now. Yep. So we got that. So if we go into our putty instance and we do 8.6. Okay. So we'll say hostname server. There we go. So we now know that we're at the server, so that's good. That's working. Do the out-of-band connection, and now we'll do the client. So Cisco for username and password. Etsy net plan. And we'll just do the same stuff here. So DHCP is going to be false. So ENS2, that's fine. But we're going to set the addresses. And this is for the client. So this will be 10.10.20.20 /24. Gateway is going to be 10.10.20.1. And we're going to set the ENS3 interface. HCP4 is going to be false. Addresses will be inside the brackets 192.168.8.5. And then gateway, it will be 8.254. So we'll have to do the same thing of sudo IP route add 192.168. Actually, we could just do a default route here. Show. IP route show. Okay, so then what we could do then, if it's already there, is we're gonna have to delete that. So sudo IP route delete default via 10.10.20.1. Sudo IP route delete default via 10.10.20.1. Okay. Because then we can get out to the internet as well as reach the host through the local network. So in case we need to add any packages, for example. Okay. So that should be handled. If we go back here, still have our reachability. We'll go back to .5. Sudo hostname client. All right, so we got our client, we got our server, and we got all of our routers. All right. So now that we got all the IPs assigned for the out of band, now we have to do the in band, which is going to be all the connectivity between the various routing elements. So let's go ahead and set that up. So for router 1, interface gig 1. So this goes to router 4. So we're going to say from router 1 to router 4. I'm going to use this scheme here. So this is, we're just going to use 10 dots everywhere. And then this is from router. This is the to router. We're only going to really care about router 1 and router 2 anyway, since those are the hosts that need to communicate with each other. And then the last octet right here will be the identifier of the router in question. So this, when we look at routes, we'll say this is the link between router 1 and router 4, and this IP specifically belongs to router 1. And on the other side, when we do it on router 4, this will be a 4. So that's kind of the logic there. So we say interface gig 2, that goes to router 3, so IP address of 10.1.3.1. And then we'll say for, let's see, interface gig 3. So this is the one that goes to the server. We're going to say IP address of okay. Then we'll bring up all the interfaces at the same time. All right, so for router 2, it's going to be the same deal. So interface gig 1. So this goes from router 2 to router 3. Wait. Yeah, we have it on this one. IP address of 10.20.1. Let's see, router 3, so 10.1.3.3. All right, so we have all 3 interfaces up on router 4. That's good. All of those are up. And all of these are up as well. So that's great. That's exactly what exactly what we wanted. So let's do some validation tests here. So from router 1, we should be able to ping to router router 3 and router 4. So if we ping 10.1.3.3 to router 3, that's good. 10.1.4.1. No, sorry, 10.1.4.4. There we go. So the first ping will always fail because, well, not always fail, but when there's no ARP entry, then the first ping will fail. There's an ARP that occurs across the link, so the router needs to learn what the layer 2 MAC address is for the layer 3 IP address that's associated with the other router. So that's the first failure that you see. But then any subsequent pings will just go through, as you can see here. So that's the reason why that fails initially. So there's nothing to be worried about. Now we should also have reachability to our local server as well. So let's go ahead and test that out. So that should be 10.10. And there you go. So same thing. So we have reachability to our local server as well. And then we're going to test the same thing from router 2 as well. So we should have connectivity from on the link between 2 and 3. We should have that connectivity, which we do. And then the link from router 2 to router 4, we should have that connectivity as well, which we do. Let's validate our server link. Perfect. Okay. All right. So that is working as expected. However, we do not have any reachability between router 1 and router 2. So if we go back and we take a look at what the topology is here, now that we have all this out the way. So router 1 and router 2 are not directly connected to each other. They run through router 3 and router 4, which are the ISPs in this scenario. So Verizon and AT&T for the sake of argument, right? So if router 1 wants to get, if router 2 wants to get to router 1, right? Like, we need to have this, we need to have the network advertised. So if we're hosting services, if we're router 1, we're whatever company, and we offer services that we sell, maybe we're offering security services and we do penetration testing and all this other stuff, right? And you may be a customer and you want to reach out to the service provider to take advantage of whatever they offer. Well, you need a way to get to them. So they have to advertise routes onto the local internet, onto the public internet. That way you can reach those services through your provider, whoever it may be. So all the major providers, they talk to each other, AT&T, Verizon, Comcast, they all have interconnections with each other. So if you're connecting to Verizon, for example, as your internet service provider, that doesn't mean the service up here has to be on Verizon. They may be on Comcast or AT&T, but because those major providers like Verizon, AT&T, and Comcast all connect to each other, that routing and reachability information gets shared so that you can access it even if you're not on the same provider. So if we take a look at this router, even if we just go to the client, right? So we see here that our IP address is the on the client side, the 20 address. So if I try to ping out to 10.10.10.10, I don't have any reachability. That's because the routes haven't been advertised yet. And you can see here, destination network is unreachable, right? So you can see here that, actually, hold on. So IP route show. All right, so that source device is wrong. So we need to fix that. So sudo IP route add 10.10.0/24 via 10.10.20.1. Okay, there we go. That was going out the internet. So that's why that showed incorrect. I don't got trace art. All right, so I'm gonna correct it here because it's probably the same thing. IP route show. All right, so sudo IP route add 10.10.20.0/24 via 10.10.10.1. All right. So even if we just take a look at pinging here, so 10.10.20.1, we'll see here that the routes are failing. The pings are failing because there's no routes for the reachability that we need in order for this communication to work. So that's the first thing that we have to do, is configure some basic BGP peering between all the routers. That way routing and reachability information can be shared. So let's go ahead and start that. So we'll say router BGP1, and we are going to advertise the network of 10.10.10.0, which has a subnet mask of /24. And then our neighbor is going to be 10.1.3.3, which is router 3. And their remote autonomous system number is going to be 3. And then we're also going to have a secondary peering for 10.1.4.4, which is router 4. And the remote AS will be 4. So we'll do the same thing for router 2 as well. Router BGP2. So when I say router BGP1 or router BGP2, this is starting a BGP instance, and this is the autonomous system number that I was talking about before. So router 2 is ASN2, autonomous system number 2. Router 1 is autonomous system number 1, so on and so forth. Keep it simple, right? So for router 2, we are going to advertise the network of 10.10.20.0, mask of /24, and then our neighbor is going to be 10.2.3.3, remote AS3, and then our other neighbor will be 10.2.4.4, remote AS4. All right, so for router 3, router BGP3, our neighbor is going to be from link to 1 to 3, router 1, which is remote AS1. Then we have another neighbor of router 2. Now, what I'm going to do here is I'm going to put in some prefixless entries. This is commonly done in the service provider environment, where you have policies in place to make sure that whoever owns the IP address is the one that's advertising the network to you. So IP addresses are something that you purchase and that you have to renew and certify that they're yours through a regulatory body called ARIN. And you have to renew those periodically, and you have to register them. So if you're a company, you would pay for an IP address, and then you can take that IP address and you can advertise that to the internet, and then it will get propagated. Service providers will filter IP addresses that do not belong to you. So if you have an IP address that you attempt to advertise to them, if it's not an IP address that is recognized as being owned by you, they will discard that update. They will not propagate it out. So this is a similar technique to what they will use. They will use a filter. In this case, it's going to be a prefix list. And this is going to say that if you're router 1, I will accept the 10.10.10 network from you because that's your network that you own. But if you try to send me something else like 10.10.20, I'm not going to let you send that to me. I'm going to reject that advertisement. And it's going to be the same concept for router 2 as well. For router 2, if you send me something, if you send me the prefix that belongs to you, which is 10.10.20, then I'll accept that. Otherwise, if you send me 10.10.10, then I'm going to reject that. So let's go ahead and set that up. What we'll say is for neighbor 10.1.3.1, which is router 1, I'm going to apply a prefix list of R1 in the inbound direction. And for my other neighbor, which is 10.2.3.2, I'm going to apply a prefix list of R2 in the inbound direction. So if I then configure my prefix list, I will say IP prefix list of R1, and I'm just going to put in some sequence numbers here because it gets read in a top-down order. I'm going to say deny any advertisements that are sent to me if they contain 10.10.20.0. And conversely, we'll say for sequence number 10 to permit or accept the advertisement if it's 10.10.10/24. And this is for router 1, because router 1 owns 10.10.10, but it doesn't own 10.10.20. And then we're going to put in a similar prefix list for router 2, where we're going to set up a deny statement right at the beginning. And we're going to say if you try to send me 10.10.10.0, I'm going to deny it. Okay, so if we take a look at the BGP and we take a look at the prefix list, so we can see here we have our two neighbors. We have this neighbor, which is the link between router 1 and router 3. And this is the link between router 2 and router 3. So this is router 1, this is router 3, router 2 rather. And we have our prefix list configured. So whenever we get an advertisement that comes in, because we do have a prefix list configured, we then need to look and check the prefix list, see what's referenced there. And we can see that for router 1, we have these rule sets put in place. Router 2, we have these rule sets put into place. So now we need to do the same thing for router 4. So we'll say router BGP 4, neighbor 10.1.4.1, remote AS of 1, neighbor 10.2.4.2, remote AS of 2, and we need our prefix list, router 1, router 1 10.10.20.0. Let's borrow some of these. So this one will deny for router 2 10.10.10. And then for sequence 10, we are going to permit 10.10.20. So if we take a look at the BGP config, okay. So now we should have full BGP peering and we should have routes being advertised. So we can validate that by doing show IP BGP summary. And we can see that our neighbors, both of our neighbors are up because they have a timer. Otherwise, this would show a status like idle or active, like it's trying to actively communicate, something along those lines. And we can see that we did get a prefix. So we did get a route received from both of these peers. So if we do show IP, BGP neighbor, and then routes, we can see what they advertise to us, which is the 10.10.20 network. So that is accurate. And we'll see the same thing for the other peer as well. Yep. And this is the ASN that I was talking about before. So remember how we said that the ASN will be appended to every advertisement. So the way that you would read this is the wait. So don't just kind of ignore that. But you can see here that you start from the rightmost value, that is the originating router, and then you make your way in. So this started from router 2, went to router 3, and then now it hit us. Same thing down here, it went to router 2, it started at router 2, it went to router 4, and then now it's at us. So all the peerings here are good. Good. And good. Okay. So all of our peerings are up. Excuse me. So we said before that there's basically 4 different things that we could do. And the first thing that we said is that we could actually do nothing. So what happens if we do nothing? If we have failover that's just baked in as part of the environment, it's something that we configure from day one to have all this diversity. You know, we have these physical connections. We have 2 different providers. If one's having a maintenance, there should be no problems, right? Well, that's not necessarily the case depending upon the configuration. So all this is very much your mileage may vary situation. But if I go in and so now I have reachability from this host, right? From the 10, from the client on the 10 network to the server on the 20 network, right? So now I have all this reachability. .10, right? Okay. So we have all this reachability, right? Now, what I'm going to do here is I'm going to let a continuous ping run, and I'm going to kill the link on the primary pathway between router 1 and router 2. So we're looking at this from the perspective, if we go back to the diagram here, we're looking at it from the perspective of router 1. So right now we're going to take actions here to shift traffic from one ISP to another ISP for router 2 down here. So router 2 right now, they're going to have some pathway that is best available for them to reach router 1. It's either going to be this ISP or this ISP. So if we go back and we take a look at router 2 and we see what the route table is, so show IP route, and then we'll filter it by saying give me 10.10.20.1. Oh, sorry, 10.1. So we can see here that the link to router 3, because remember this is from router 2 to router 3, is the primary pathway. So we can see here we have 2 and just kind of expanding out on this on the BGP table. So if we look at the BGP table itself, we'll see that for this network, we have 2 different available pathways. We have a pathway through router 4 and a pathway through router 3. And the one through router 3 is the one that is currently the best path available because of this little caret right here. So whenever you have that caret, that means that this next hop is where the traffic is going to go. It is the best pathway that is available. So the question becomes, what happens if that pathway becomes unavailable and traffic needs to go through router 4? So what we'll do is we will get our ping started here on the client side. So this is going through router 3, right? So if we go to router 1, what happens if we go there and we kill that pathway through router 3? Let's take a look at that. So we said that in our environment, from router 1 to router 3 is gig 2. So what we're going to do is we're actually going to shut down that gig 2 interface. Interface gig 2, shut. So BGP went down on router 1 because that link is down, right? We see it's administratively disabled. So let's take a look at router 3 now. We don't see the interfaces being down yet. And our peering is up. But look what happened here with our ping. So even though we took action at the server side, right? So even though we went into this router right here, router 1, and we took this link and we disabled it, which should have traffic coming in over this way. That's not happening. Traffic is still coming in through this way, and it's currently breaking. So why is that? Well, if you take a look at this output, you'll see that the interface is down on router 1, but on router 3, the interface hasn't reflected as being down yet. And the BGP neighborship is still showing as being up. So because this BGP table, because this router still thinks that it has an active communication pathway from itself to router 1, it's still going to propagate routes downstream to router 2. So even though that the link isn't actually there, because the protocol itself believes that things are still functioning as expected, it's causing traffic to get black holed, and this client can no longer communicate. Now, a common cause of this is due to actually BGP timers. So the way that BGP operates is it sends a hello timer every 60 seconds by default. And if it doesn't get 3 of those hello timers back over that time period, then it tears down the neighborship manually. So what that means effectively is that you have a potential 3-minute window where you could take an outage because you didn't recognize that the link is no longer available. See here, now we just started to get our pings back. So out of 187 packets that got transmitted, only 55 were received. We had a 70% packet loss rate right there. You can see here that we had the initial sequence where we were pinging all the way up to about 40, and then we didn't get anything back until about 175. So now if we go back to router 3, we should see that even though the interface is still up, now BGP is down. And once that happened, then that kicked over the propagation, right? That kicked over the traffic from taking the router 3 pathway to taking the pathway through router 4. So no longer is traffic going through this pathway here. It's now going through this pathway. Now, commonly timers are modified to be a bit more aggressive. And that will reduce the amount of time it takes for something like this to happen. So you can shorten it from the defaults, which is 180 seconds for the whole timer to expire. So 3 minutes. You can shorten that. Commonly, what's seen in the service provider realm is 3 seconds for a hello and then 9 seconds for your dead interval. So after basically 10 seconds, the peering will tear itself down and pings will start working again. However, as you can see, that may not be the best approach. You may want to take some actual action to fail traffic over. That way you have more control over your environment and the availability. So let me go ahead and bring this link back up. All right, so we can see that BGP has now come back up. And okay, so we're good. We're back to the state that we were in before, except now traffic is just going through the other router, which is fine. So what could we do to help prevent this? So if we zoom out, right, like what we're trying to accomplish is that we're a service provider. We want to make sure that we have high availability that's available for our environment. So we talked 3 different methods. The first is revoking the advertisements. The second is making our routes look worse on one link versus another. And the third one is using community tags, which could be something like making our routes look worse or making our routes look better, depending upon what you configure with the remote host. So let's take a look at the first one. So what if we want to revoke our advertisements? So if right now we take a look at router 1 and we do show IP BGP, we see that we have both of our routes available, and the best one is through router 4 right now. So if that was the one that was taking the maintenance, and we wanted to remove our routes from that pathway, and so it doesn't matter if the link goes down, it doesn't matter if the BGP peering goes down, we're not relying on that. What we're going to do is we're going to push an update to our BGP peer, and we're going to say, look, this route through this pathway looks really, really bad. Don't use that pathway. Come into our network through the other way. So how can we do something like that? What we can do is go into our BGP instance, and let's see, we want to make the router 4 pathway look bad. So what we'll do is say for our neighbor to router 4, we're going to apply a prefix list of R4 in the outbound direction. And in that prefix list, and this is going to be similar to what we did before, we are going to say prefix list is router 4, and we're going to, I'll put a sequence number anyway. I'll just say deny the 10.10.10.0 network. So what are we doing? We're saying that for our neighbor, we're applying a prefix list in the outbound direction. So that's the advertisement direction. And when we look at that prefix list, it's saying, don't advertise this network. Now, if we take a look at router 4, where we're sending that, and then what I'll do here is I'll start up another ping test to get that going. If we take a look at router 4, we now see that, sorry, hold on. We'll now see that this got retracted. We are no longer getting that prefix from router 1. I probably should have started that ping test beforehand. So let me go ahead and actually revert that. So router BGP 1, no. Okay. So clear IP BGP. There we go. So that clear IP BGP command is just to reprocess the outbound advertisement to our peer. So let's go ahead and set this ping back up like what we had going before. So if we take a look at show IP BGP neighbor summary, we got 2 peers, and we have so we are preferred through router 4. So if we take a look from router 4's perspective, we have 2 prefixes that are being advertised. So this is from router 1, so we can actually look at this. Show IP BGP neighbor, this guy, routes. So this is the route that's being advertised to us from router 1. So if we go back and we apply, and we have our ping running in the background so we can see if there's any impact here. So if we go back and apply this, so notice that we still have our route inside of router 4. The BGP update doesn't take effect immediately. It will periodically refresh. I believe it's like every 30 seconds or so, but you can kind of kick the process by doing a clear command You have to be careful with this in production environments because you could actually tear down the BGP peering if you're not careful. But if you do clear IP BGP followed by the peer, and then you do soft out. So soft is a soft reset of the peer, meaning that you don't completely tear down the underlying TCP communication pathway between the peers. But what you do is force the router to redo the logic for either the inbound or outbound modifications that you're making. So in this case, I'm telling the router, recalculate your outbound advertisement logic. And in this case, it's going to lead to this prefix not being advertised. So if I go back and look at router 4, now I see that there is no prefix being learned from my peer, which we can confirm here as well. And then if we go back to our ping that we were running this entire time, we'll see that we didn't actually lose any packets. And that's because the BGP table in router 2, as it was trying to communicate with the upstream networks, it had both of these routes at the very beginning, right? So it always knew that if this pathway isn't available, I can just use this pathway here. So as soon as that change gets propagated throughout the network, it already has the next hop available for the second best pathway. It doesn't have to do any sort of recalculation on the fly to say what is the best pathway available to me now that this route is not available. So it had that route, it had two different pathways that can be used for that network. One went away, so it just knows I'm just going to use the other. So if we take a look at this BGP table now, we can see here that the pathway through router 4 is just missing. It just went and started using router 3 immediately. So when it comes down to revoking the advertisement from that ISP, we can see that it takes effect without having any sort of impact from the transit perspective. So any sort of traffic that was going over the internet, going over that link, was really not affected because everything just shifted over to the other link. So this is how you can drain traffic over time before that maintenance hits, and you don't have to worry about a production impacting event. So let's go ahead and revert this change. So no neighbor. Then we'll say no IP. And we'll get rid of this too. We'll go ahead and clear. Got our prefixes back on router 4 and on router 2. We now know about the pathway again. But you notice how it's stuck to that router 3 pathway, right? So originally, router, where is it? Actually, router 3 was a pathway that we needed to filter. Alright, so that's an invalid test then. I'll go ahead and I'll prove it out again. So the pathway through router 3 is what we actually needed to test. I'll just do it here real quick to kind of prove my point. Neighbor 10.1.3.3, prefix list R3 out. IP prefix list R3. Sequence 5 deny 10.10.10.0/24. Okay. So it's still there. All right, so here 3.3. So the pathway through router 3 was the primary pathway. Now we just went to router 4. Let's take a look here. We didn't lose any pings, right? Just like I said before. So same logic, just wrong peer that it was applied to. So yeah. All right. So we'll go ahead and this out since we don't need it anymore. So this was retracting the advertisement from the ISP. Okay. So what if we didn't want to do that though? What if we didn't want to retract the advertisement, but we wanted to make the route look really, really bad and make it look less attractive than one of the other available pathways? So that is something that we can do if we wanted to do it. So let's take a look at what that would look like. I'm going to run this ping so that we're ready to go. So let's see. From router 2's perspective, the pathway we're taking is going to be through router 4. So that's the pathway that we're going to make look undesirable, right? So what we're going to do is very similar to what we just did, but it's a little bit different with the way that we have to put the pieces together in terms of using the prefix list. So what we're going to do is we're still going to use the prefix list. So we're going to say IP prefix list. What was this, router 4 I said, I think? Yeah, so router 4. Sequence 5. But this time we're going to use a permit statement because we don't want to block the advertisement. And then what we're going to do is we're going to create a route map. So we're going to say route map R4, and I'll just do R4 peer just to, make it distinguishable that this is, even though you could name the route map the same thing if you wanted to, I'm just going to put in a little bit of a distinguishing feature here. And then we're going to say permit 10. We're going to match the IP address of prefix list R4, and we're going to set the AS path, and we're going to prepend it with our own ASN. You always prepend with your own ASN. Otherwise, you could risk routes being rejected by the upstream providers. Okay. So logically, what we're doing here is we're saying, okay, so we have a prefix list. We're going to match the prefix that we're advertising. So that's done. And then what we're going to do is put a whole bunch of prepends to the back of it to make the route look really, really bad so that you don't want to use it. So now we're going to go into our BGP instance, and we're going to say for our neighbor 10.1.4.4, we are going to apply the route map of the R4 peer in the outbound direction. So remember before I said that this is the ASN value here. So this came from router 1, went to router 4, and it's now here. So let's go ahead and clear our neighbor. So we'll go ahead and do that. Now what do we see here? So we see that the ASN has been changed to now have not just one number ones, but 6 number ones. So, and you can see how the preferred pathway changed as well during this time. So this was the output before. We actually preferred route 4, the pathway through router 4. However, now that we see the prepend has taken place, this caret has flipped from router 4 to the router 3 pathway because the router thinks that there are more hops that need to be taken in order for us to reach this prefix. Now, if we take a look back at our ping test, again, we didn't lose any pings, right? Because we had those routes. They were always there inside of the route table. So it just flipped from one entry to the other. So that's how you would do something like an AS path prepend, where you don't retract the advertisement, but you just make one of the advertisements, kind of just look really, really bad, right? Okay, so do this. So we will say no neighbor this. We will get rid of the route map. We'll get rid of the prefix list. And now we're back to normal. Except this time we're still preferring router 3, which is to be expected. Okay. So now that we have that done, so we've explored doing nothing and we've seen the impacts to that. We've used the outbound prefix list where we revoked the advertisements. We used a route map to not revoke the advertisements, but to make one pathway look worse than the other. Now, the other option that we have available, the last one that we have here, is the community tag. So the community tag is as I described before, it's a value that gets associated with the route. So if I take a look for router 2, actually this would have to be on the router that it's received on. Well, it's trans. Anyway, so we'll look at router 3 for this. 10.10.10.1. So we can see that there's no community tag associated with this route, right? So a community tag is a way that we can mark a route and we can have a predetermined agreement with that carrier. So if you and I were peering, we can have an agreement that says, hey, if you tag your route with the number 50, then I'm going to do X, Y, or Z. So we can say that, hey, you know that prepending thing that we just did? If I give you a route and it's tagged with 50, then I want you to do that prepending with your ASN and make the pathway through your network look worse than all the other networks that I peer with. So that's a way that you can push a BGP update without prepending yourself, but you can have it as a stipulation of that peering agreement that if I do present you with this community value, then you're going to do the AS path prepending and make my route look worse through your network and effectively force traffic in through the other providers that are out there. So that is something that can be done. It just needs to be coordinated. That way it'll work because you need configurations on both them. So let's take a look at how we can do that. Let's see. So for router 1, we're going to say so this is through router 3, 10.10.10.0, and then we're going to create our route map just like we did before for the R3 peer, and we're going to match the IP address of the prefix list R3, and we're going to set the community, and I'm just going to do something simple, 1:1. This value is typically predetermined ahead of time, so you wouldn't just make this up on your own, but this will do for all intents and purposes here. So excuse me. So now that we did that, router BGP1, map, you're out. Now the additional command that we need to run here is 10.1.3 send community. So it's not just enough for this particular scenario to apply a route map saying to do these things. You also have to explicitly configure the neighbor to have the capability to send those community values to the peer. Okay. So that's done on the router 1 side. So router 3, if we take a look, Now we have that community value here, right? So we can see before we didn't have a value, but now we have this value. But even though they sent us that value, nothing has happened. Nothing has changed. So I'll get a ping going here, but if I take a look over at router 2, my route table looks exactly the same. My 10.10.10 network, I'm still going through router 3 right now, just like I was before. So what we have to do on router 3 is we have to configure our router to, when it sees that community, take some sort of action. So in this case, what I need to do is first actually define the community value. So a community list is basically an access list, if you want to think about it that way. So we're going to say that this is access list 1, and we're going to permit the community value that we just previously configured. And then what we'll do is configure a route map for the R1 peer. And we will say we're going to match community 1. And then we're going to set AS path prepend. And then this time we're going to use our ASN for router 3, which are 3s. Now, what we need to do is apply this in the inbound direction on our BGP instance. So router BGP3, neighbor 10.1.3.1, route map of R1 peer in. And then we'll do clear IP BGP for our peer soft in. So remember, we have to either wait for that update to come in through to us again, or we can just kick the router and say, hey, for this BGP peer, I want you to rework the logic in the inbound direction. So if you're receiving a route, now you see that it has a community value. Now you know that you need to prepend with all of this ASN value. So if we take a look back at router 2, now we see we have all of these prepends, right? So we have the 1. Remember, we start all the way to the right. We can see that this route started in the ASN number 1, which is router 1. And we could see here as we're going through this ASN pathway, it gets prepended 6 times from router 3, which is what we configured it to do, before it landed in our network. So we swung our traffic from this preferred pathway here through router 3 over to the other preferred pathway, which is now router 4. And if we take a look back at our Ubuntu host where we were running that ping, we can again see that we didn't lose any packets during this time period. So we were able to effectively steer traffic from one ISP to another without losing any of the traffic like we were before if we were to just tear down the links and do a physical teardown of the peering itself. Okay. And then also to show that this is a transitive attribute, if we take a look at the route, let's see. Okay, yeah, it's not showing up. That's weird. Put the research up, but not too worried about that because this, yeah, this is irrelevant to the overall discussion that we're having. So the other thing I haven't brought up during this time is BFD. So bidirectional forwarding detection is another method that can be leveraged. However, that's typically used not within a ISP peering. So when we have this scenario here where we have 4 different routers, um, all of these routers are not owned by us, right? So if we are the service provider at the top here, right? So this is us right here, router one. This is the only router that we own. We don't own any of the other ones. So if we want to set up something like bidirectional forwarding detection, that's a independent protocol that runs on links between routers. So for example, here or here is where you would run that BFD instance. And you can use that as a mechanism to basically have sub-second failover at a protocol level. So before, when we were talking about BGP and how there are hello intervals where there's communication that occurs, for example, between router 1 and router 2, say using this pathway, or even this pathway here, right? Because there's two different pathways that it can happen, where the advertisements can get propagated, even though, so the peerings are between this router and this router, but logically the routes that get exchanged between the routers are directly between 1 and 2 here. So if there was a failure that occurred, we would want to take a look at the individual links between the two routers, which would be either here or here. And while that can be leveraged for sub-second failover, so instead of waiting for the BGP timers where it's either 3 minutes for the whole timer to expire or up to 10 seconds if you're a bit more aggressive on the timers, you can get something like sub-second failover using BFD. So there's a protocol that runs between these two hosts, for example, right here, where you can detect a link failure and tear down that BGP neighborship in a much quicker time than what you would typically anticipate being available to you. However, that's something that needs to be configured on both ends, similar to the community strings that we were going over before. So if you don't have control over the remote end, and typically this is not something a provider will do with you, like how they may support your ability to use a community string, they typically don't support any sort of BFD detection. That's usually something that's going to work internally within your network, where if you have a string of multiple routers that you control and you want to have sub-second failover within your own domain, you can do something like that. But when it comes to the external peers to the internet and so forth, that's not something you would typically see for a BFD deployment. So just an honorable mention there. I figured I'd throw that out there. That's the reason why it wasn't included. But let's see. We've been live for about an hour and a half, and that actually covers everything. So we went over, like I said before, what BGP is, and logically what it provides. We went over the architecture and stepped through the configuration. If you guys find this information useful, please let me know. I'll probably end up posting a video on it as well. If you like these live formats where I kind of set up the lab and show you how everything is configured and then kind of step through it, I can continue to do more of them. Just, leave a comment and let me know. But otherwise, have a